Welcome to Lecture 1.5, Multisets and Multi-Choosing. To motivate this topic, let's consider an n-element set S. Think of a group of n people. We can construct several things. First of all, we can construct lists from S, where order matters. So this is where we want to pick a president, vice president, and a secretary. Or maybe we have a 15-person baseball team and we want to pick a 9-person batting order. So who bats first, who bats second. So these are lists where order matters. We can also construct sets from S. So order doesn't matter. So we want to pick 3 at-large members for a committee. Or we have a baseball team of 15 people and we want to select 9 who start the game, and we don't have to worry about batting order or position. So those are things we can construct. We can also count these things. So if we want to count the number of lists of length k, well, there's actually 2 cases. If repetitions are not allowed, like in the baseball example, then there are n choices for who goes first, n minus 1 choices for who goes second, all the way up to n minus k plus 1 choices for who goes last. And if you multiply this out, it is n factorial divided by n minus k factorial. However, if we allow repetitions, then we get a bigger number. So instead of multiplying k numbers together that start with n and go down, decrease, we're multiplying k copies of n together. So imagine the scenario now where we have n people and we have k different chores. So we can assign, there are n choices for who does the dishes, and then there are n choices for who cuts the lawn, and n choices for who does the laundry, and so forth. Because the same person is, in theory, allowed to do all of the chores. That doesn't make sense in baseball. You can't have the same person bat first and bat second and bat third, or be pitcher and catcher. So for the chore example, repetitions are allowed. For the baseball example, repetitions are not allowed. If we want to count sets of size k, then again we can either allow repetitions or not. If repetitions are not allowed, which has been our default assumption, so if we want to pick k people from n to serve on a committee, or pick k people from n to start on a sports team, then it doesn't make sense to allow repetitions, and the number of ways to do that is n choose k, which is n factorial divided by k factorial times n minus k factorial. It's this number up here, the number of lists or permutations, divided by k factorial to count for the overcounting. We don't know how to count this if we allow repetitions. And in this lecture, that's what we're going to do. Now, a set with repetition is called a multiset. And let me first give you an example of what this might represent so you can have a better sense as to what we're doing. So normally with the set, if we have the set containing 1, 1, 1, and 2, we don't allow repetition, so this is defined as the set containing 1 and 2. However, consider the case where we have a collection of objects and we allow repetition. So maybe we are, instead of picking 9 people to be in a baseball game, we are picking 9 drinks for those people, for those players. So maybe 5 of them want a Coke and 4 of them want a Sprite. So it obviously is not going to make sense to call this collection of 9 elements to call it a set, because then it would just be a set of 2 elements, C and S. So we don't want that. So we're going to call this thing a multiset, and we don't want to use the same braces either. So there's really no one good convention for what multisets are usually denoted by. So I'm going to use angle brackets in this lecture. It's not perfect, but it's different enough that it should be fine. Now that we know what a multiset is, let's define this notation. So it's like n choose k, but with 2 parentheses. We call it n multi-choose k. let that be the number of k-element multisets on an n-element set. We will write multisets as I did in the previous slide using angle brackets rather than curly brackets. And notice that unlike for combinations, k could be larger than n. So I just gave you an example of where we're picking 9 drinks from a vending machine of 15 flavors. But I could also pick 25 drinks from that vending machine. Or I could pick 15 drinks from a vending machine of 9. So I can write things like 9 choose 15, and this is going to be a lot bigger than 0. This is the number of ways to choose 15 different drinks from a vending machine of 9 flavors, whereas the number of 15 element subsets of a size 9 set is clearly equal to 0. Let's do a quick warm-up. So consider the following set, S equals A, B, C, and D. How many 2-element sets can be formed from S, or subsets? So those are going to be A, B, A, C, A, D, B, C, B, D, and C, D. So that's 6. So how many 2-element multisets can be formed from S? So now picture that these are 4 flavors in a vending machine, and we want to pick 2 of them. So we have A and A, so we can pick 2 A's. We can pick an A and a B. We can pick an A and a C. And we can pick an A and a D. We could also pick a B, 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 C, B, D. We could pick a C, 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 D, or we could pick a D, D. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the answer for there is 10. So it's not clear how to count these, what a general formula is going to be like. So that's one of the first things that we're going to do. Let me just quickly rephrase the question that I just asked. The first one, instead of how many 2-element sets can be formed from S, I'm going to ask how many ways can we choose 2 elements from S. The answer, of course, is 6. And then the second part, how many ways can we multi-choose 2 elements from S? And we just answered that to be 10. So now we're going to figure out where this number came from and how to find a general formula for this, rather than just the special case when n equals 4 and k equals 2. And here's the answer. The number of k-element multisets on an n-element set, which we define to be n multi-choose k, is actually n plus k minus 1 choose k. The proof of this is both very clever but also very simple once you see the trick. So we will encode every multiset using the so-called stars and bars notation that I actually introduced in the previous lecture. So if you have not watched that lecture, please do so first. So I think I should show this to you with an example. But basically, each star is going to represent one of the k elements that we're going to choose, and the divider, the vertical lines or the bars, these things represent the dividers between the different elements. So let me start with the example of the vending machine that I said before. So an example is a vending. So the example is not part of the proof, but this is sort of my scratch work to motivate the proof. So consider a vending machine with n equals, let's make this small. So say n equals 5 flavors, and we're picking K equals 9 drinks. So in this case, we want to know what 5 multi-choose 9 is. Okay, so I'm going to represent the 5 flavors with 4 bars. So this first one represents, say, Coke. The next one represents, say, Sprite. The next one represents Fanta. And then the next, say, what else is out there? The next one represents, say, Dr. Pepper. And maybe the last one represents water. So if we want to represent, so if we want to pick 9 drinks, let's say maybe we pick 3 Cokes, 1 Sprite, no Fantas, 2 Dr. Peppers, and 3 waters. So I can uniquely represent every choice of my drink selection. In other words, every multi-set, every K9 element multi-set from this set of 5 elements with a string of bars and stars. So notice I have K bars and N minus 1 stars. So recall from the previous lecture that N multi-choose K is the number of length. So how long is the string of characters? It's K plus N minus 1. So length N plus K minus 1 strings on N minus 1 stars and K bars. And that is one of those multinomial coefficients. And precisely, it is the length of the string factorial. So that's going to be N plus K minus 1 factorial divided by N minus 1 factorial times K factorial. N minus 1 factorial times K factorial. And notice that that is precisely N plus K minus 1, choose K. Or if you prefer, N plus K minus 1, choose N minus 1. Okay, so that's it. We turned our mysterious, our unknown problem into something that we know how to do, namely counting the number of strings of length N plus K minus 1 with K of of one character and N minus 1 of a different character. Let's do 2 examples that are related. First of all, suppose you want to buy 3 hats and there are 5 colors: red, green, blue, yellow, and orange. How many possibilities are there? And then I'm going to switch the numbers and say, suppose you want to buy 5 hats and there are 3 colors. How many possibilities are there? First of all, take a quick moment to ask yourself, which one of these is going to be a bigger number? If you want to buy 3 hats with 5 choices each, or 5 hats with 3 choices each. Okay, let's figure it out. So the first one, so you want to buy 3 hats from 5 choices. So that's 5 multi-choose 3, which is 5 plus 3 minus 1, choose 3, which is 7, choose 3. And that's 7 factorial over 4 factorial times 3 factorial. And so that's 7 times 6 times 5 divided by 3 times, 6 factorial is 6. And so the 6 cancels with the 6. And we get 35. The next one is 3 multi-choose 5. We've got to be careful. It's really easy to mess up with what is N and what is K. But here we are picking 5 things from 3 different selections. Think of the vending machine. We're picking 5 drinks from 3 flavors. So now we have 5 plus 3 minus 1, or 3 plus 5 minus 1. Choose 5. And this is 7, choose 5. This is slightly different. This is 7 factorial divided by 5 factorial times 2 factorial. So this is 7 times 6 divided by 2. And this is, that's 42 on top, divided by 2 is 21. So there's actually more choices for the first case when you have 3 hats from 5 different colors. And notice that unlike regular binomial coefficients, n multi-choose k is not equal to k multi-choose n. Let me now do a second pair of examples. First, how many ways can you buy 6 sodas from a vending machine with 8 flavors? And second, how many ways can you buy 7 sodas from a vending machine with 7 flavors? Okay, so take a moment to guess which one of these you think might be bigger. And you got it? Okay, let's check. So the first one is we are buying 6 sodas from a vending machine of 8. So that's 8 multi-choose 6, which is 8 plus 6 minus 1, choose 6, which is 13, choose 6. And then the second one is how many ways can you buy 7 sodas from a vending machine with 7 flavors? So that's 7 multi-choose 7, which is 7 plus 7 minus 1, choose 7, which is 13, choose 7. Now you see what I did? These are equal. 13 choose 7 is n choose k is n choose n minus k. So in this particular case, if this is k and this is n, then n multi-choose k is equal to something else. So the 7 here, now it's not clear here whether this 7 is this going to be a k plus 1 or is this going to be an n minus 1? So did that 7 come from adding 1 to here or subtracting 1 from here? And same thing over here. Is this 7, is that 1 less than this or 1 more than this? Okay, so that's what I want to answer next. Let's call this a theorem. I claim that for any n and k, at least 1, we have that n multi-choose k equals k minus 1 multi-choose n minus 1. I will show you 2 distinct proofs of this. First of all, an algebraic proof. Let's just write out the formulas. N multi-choose k is n plus k minus 1, choose k. And now remember the identity that n choose k equals n choose n minus k. So in this case, this is equal to n plus k minus 1, choose that minus that. So what is that? You see how that's n minus 1? Let's write it out. N plus k minus 1, choose n minus 1. And now let's go backwards. Let's go from here to here. This is equal to k plus 1 multi-choose n minus 1. If you didn't quite see how to go from here to here, let me at least convince you that if you go backwards, it absolutely works. So remember how to do that. The formula for this multi-choose that is just, we add those up, so we get k plus 1 plus n minus 1 minus 1, choose n minus 1. We just copy over the bottom. So if we do this, notice that the plus 1 and the minus 1 cancels, and we indeed get n plus k minus 1 up here. Choose n minus 1, which is down there. Now I want to do a combinatorial proof of this. So we will count something two different ways. One way using the left-hand side and another way using the right-hand side. Okay, so basically we're going to switch the role of bars and stars. So let me show this to you explicitly. So n multi-choose k is the number of length n plus k minus 1 strings or words on or with n minus 1 bars and k stars. So let me show you with an example up here. So let me do the example we did before where we had 5 multi-choose 9. So we had 4. So we had a string like this. We had 3 Cokes, 1 Sprite, 0 Fantas, 2 Dr. Peppers, and 3 waters. So here we had a string on, again, just to remind you, n minus 1 equal 4 bars and k equals 9 stars. So what I want to do now is take this string and just switch the bars and stars. So, explicitly make these 3 bars, make that a star, make this a bar, make these 2 things stars, make these 2 bars, make that a star, and make these 3 things bars. And now what we have is we have k equals 9 bars and n minus 1 equals 4 stars. So think back to the vending machine example. This is the case where we are picking 4 drinks from, we have 9 dividers, so 10 possible flavors. So this is, so again, we are picking 4 drinks from 10 flavors, or in general, this is the case where we are picking n minus 1 things from k minus 1 different flavors. So this is a combinatorial proof because, so let me write this down here. So n multi-choose k is the number of length n plus k minus 1 strings on n minus 1 bars and k stars, which is equal to the number of length n plus k minus 1 strings on n minus 1 stars and k bars. It doesn't matter whether we call these bars and stars or x's and y's or stars and bars or whatever we call them. And we know that this is by definition picking n minus 1 things from k plus 1. Because again, the number of bars, those are dividers, so there are k plus 1 regions. And that's the end of the proof. Let's summarize what we've learned so far about multisets and compare it to what we already know about permutations and combinations. We can count various size k collections of objects from a so-called universe of n objects. And there are several different cases based on what the setting is. So if we want to count lists or ordered objects, if the order matters, then, well, there's 2 cases. If we allow repetitions, then we get n to the k possibilities. This was the case when we had n people we want to assign them to k chores. There's n choices for the first chore, n people who can do the first chore, n people who can do the second chore, and all the way up to the kth chore, so we get n to the k choices. If we do not allow repetitions, then we get permutations. So like with the batting order, we have n choices for who bats first, n minus 1 for who bats second, and so forth. So then we get n factorial over n minus k factorial. However, if our collection of objects are unordered, then we get sets or multisets. So if we allow repetition, then we get multisets. So this is where we are picking k different drinks from a vending machine with n flavors. So we get n multi-choose k, which is n plus k minus 1 choose k. That was the new thing in this lecture. Compare that to the case where we do not allow repetitions, in which case we get not n multi-choose k, but n choose k, which is n factorial divided by k factorial times n minus k factorial. Let me now turn my attention back to the multiset case, because that's really the focus of this lecture. And I want to show you a whole bunch of different ways to think about multisets, of what they count. Everyone has their favorite. It should be no surprise that my favorite is the vending machine example. But I think it's helpful to see a variety of examples to compare and contrast them, and perhaps you like a different one better. So the quantity n multi-choose k, well, it counts, first of all, the number of ways to put k identical balls into n buckets. So this is sort of the opposite of the vending machine. The vending machine, we are taking them from buckets. And I guess the cans are not identical, but if we want to be able to tell which bucket they came from, we give it a different flavor, like Coke versus Sprite or Fanta. Next, the number of ways to distribute k candy bars to n people. And the candy bars are identical. So this is really the same as the previous one. So instead of balls, we'll call them candy bars, and instead of buckets, we'll call them people. But you still have a very different mental picture. Of course, I've told you about the number of ways to buy k sodas from a vending machine with n varieties. Or if you prefer, you can think of this as the number of ways to choose k scoops of ice cream from n flavors. Okay, let's change more than just the cosmetic appearance of what the product is and where it's coming from. This also counts the number of non-negative integer solutions to the following equation: x1 plus x2 all the way up to xn equals k. And finally, it counts the number of positive integer sequences, a1, a2 up to ak, that are non-decreasing. So a1 is at least 1, a2 is at least a1, a3 is at least a2, and then ak is no more than n. Okay, so let me justify the last two for you, and I'm going to show you that same example that we did before, where we had 9 different sodas from 5 different flavors. So we have 3 Cokes, and we had 2 Sprites, then we had no Dr. Peppers, then we had, no Fantas, doesn't really matter though. Then we had 2 Dr. Peppers, and then we had 3 waters. I think that was it. Okay, so what's this first thing represent in this picture? So we have n different things. So the n represents the number of flavors, right? And we are adding up n things that should add up to k. So the natural thing here is we're adding up how many choices from each flavor. So we have x1 equals 3 Cokes, x2 equals 2 Sprites, x3 equals 0 Fantas, x4 equals 2, and x5 equals 3. Notice that x1 plus x2 plus x3 plus xn, all the way, in between, equals k. So that's what a non-negative integer solution is, every such solution describes a unique multiset and vice versa. Every multiset corresponds with a unique solution. Okay, next, the number of positive integer sequences, like this. So now we have k of these. So what we are doing is for every one of these k objects, we are annotating which bucket it's in. So bucket or which flavor it is. So for example, this first one, so A1, the first choice is from flavor 1. The second choice, A2, is from flavor 1. A3 equals 1. Then A4 equals 2. A5 equals 2. A6 equals 4. A7 equals 4. A8 equals 5. A9 equals 5. And A10 equals 5. So notice that by construction, the sequence is always going to be non-decreasing from 1 to n. And again, every sequence corresponds with a unique multiset and conversely. Okay, so I hope this helps you to just expand your set of ideas for what the things that multisets count. Some of these are going to be more useful than others if you want to explain it or compare it to something else in combinatorics. I want to conclude this lecture by revisiting a familiar concept, that is combinatorial proofs. So sometimes there are different ways to count the same set of objects. This can lead to two different formulas, often very different looking formulas, that are secretly the same. We call this a combinatorial identity. Verifying an identity by counting a set two different ways is a combinatorial proof, and that's going to be the main topic of the next lecture. But first, we'll see an example of this involving multisets. And here is that example. You have 11 biographies and 8 mysteries that you want to arrange on your bookshelf, but no two mysteries can be adjacent to each other. How many different rearrangements are possible? So I'm going to draw a picture of this, because this is one of those problems where there's no obvious right first step. So you sort of have to play around with it and try something and see if that works. So I'm going to draw 11 biographies, or 11 B's, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Let's just first focus on these. Forget about the mysteries. The books all have different titles, so let's just suppose that they're numbered. So maybe this is like B1, maybe B2 is there, 3, 4, 5, 6, 7, 8, 9, 10, 11, something like that. And now let's stick the mysteries on the shelf. So the mysteries, because they cannot be adjacent to each other, you can put at most one mystery in each of these gaps. So how many gaps do we have? So we have, let me see now, let me use a different color. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 gaps, and we have 8 mysteries. So one way to do that is put a mystery here, M, 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 so 1, 2, 3, 4, 5, 6, 7, 8. So suppose we do that, and now of course the mysteries also have titles, but let's just make those numbers. So maybe the ordering is 1, 2, 3, 4, 5, 6, 7, 8. So let's count the number of ways to do this. So first of all, there are 11 factorial permutations of the B's, of say the column BI's, or just the B's. So there are 11, so if you ignore the mysteries and just look at the ordering of the blue ones, there are 11 factorial ways to do that. And then we are, what we're doing is we have 12 gaps, and we are filling 8 mysteries in those gaps. So we have 12 choose 8 ways to fill the gaps with the M's. I'll just call them M's instead of MI's or MJ's. And then once we fill those gaps, we have 8 factorial ways to permute. Or once we determine which gaps are filled, there are 8 factorial permutations of those M's. So times 8 factorial permutations of the M's once those gaps are chosen. So overall, this is 11 factorial times 12 factorial over 8 factorial times 4 factorial times 8 factorial, and we get 11 factorial times 12 factorial divided by 4 factorial, and that's approximately, I think, 7.97 times 10 to the 14th. And I'm really just focused on this expression here. Doesn't matter exactly what this is. It's a big number. And now one more comment is, so this product of these two things, this can be simplified. You may notice that this is actually the formula. Well, let's see, this is 12 factorial divided by 4 factorial, which is the number of permutations of picking 8 things from 12. So we could have done that from the start. Maybe I should have used red for this because, because these are actually the mysteries. So let's think about why we could have counted them that way. So picture the M titles of the mystery 1 up to 8 as the batting order. So this is gap. Let me use another color. So this is gap 1. Oh, that's not a great color. Let me see if there's a. I'll just use black here. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So what we're really doing is by assigning the mysteries to the gaps, we are coming up with a permutation of 8 of the gaps. So for example, this permutation here, or the particular one that I did, is starting with 5, 4, 2. So let's write this down. So this is 5, 4, 2. And then 4 is 11. Maybe I should put commas in here. 12 is the next one. Then 9, then 8, and then 6. So what we're basically doing is picking an 8-person batting lineup from 12, a team of 12. So yes, that could have been counted like this. However you want to do it, you get this formula. But now I want to show you a different way that you could have done this. So now let's first, instead of sticking out the 11 biographies on the book, let's first put the mysteries on the bookshelf. So let's do M 1, 2, 3, 4, 5, 6, 7, 8. Now the requirement that these have to be right next to, or that they can't be next to each other, it means that there has to be at least one biography between them. So I'm going to consider the space immediately next to each mystery, which I claim has to be filled with a biography. So I'm going to stick a biography in there, B1, or I'm not going to put a subscript. So let's put biographies in here, like this. So we have to have some biography there. And then what we're going to do, let me pick a different color, is so these things are blocks, they don't move. So once we have these 8 blocks together, now we have 4 more biographies, 3 more biographies that we have to stick in these. Oh, I'm sorry, let me fix that. We don't actually need a biography at the end here, right? Because The only reason the biography is here is so these two mysteries don't go together. So let me actually cross that out. And now let's look at what we have. Well, we have let me use a different color. We have 1, 2, 3, 4, 5, 6, 7, 8, 9 possible gaps for the remaining 4 biographies, because we've only actually put 7 here, because the last one doesn't necessarily get a biography on afterwards. So let's write that down. So there are 8 factorial ways to arrange the m's, permutations if you prefer. That's the first step. Then we have P of 11 set. So we are picking a batting order of size 7. So we are picking 7 from 11, which is 11 factorial over 4 factorial ways to put the b's next to the m's. We don't need to do the last one, remember? And finally, no, I guess it's not quite finally, then we have 4 remaining books in 9 gaps, and we can put all of them in the same gap if we want to. So this is actually a multi-choose problem. This is 9 multi-choose 4, which is 12 choose 4, which is 12 factorial divided by 8 factorial times 4 factorial. And finally, once we put those 4 extra biographies in there, let's see, how do I want to color them? Let me color those extra biography. Oh, I'll do this. So there's one, there's another, and maybe there's 2 actually go right here. So once we actually decide where those things go, then there are 4 factorial ways to permute them. Oops. Permute to permute them. So again, once we figure out where, so for every possible multi-set, arrangement of stars and bars if you prefer. So here the bars are right here. Then there are 4 factorial ways to arrange those 4 things. So we should be getting the same thing. Let's check that we actually do. So in total, we get 8 factorial. So we're just going to multiply these numbers. So we get 8 factorial times 11 factorial divided by 4 factorial times 12 factorial over 8 factorial times 4 factorial times 4 factorial. And indeed, these things cancel, those things cancel, and then we get 11 factorial, 12 factorial over 4 factorial, and indeed that checks out. So this is an example of where we count the same thing 2 very different ways, and we get 2 very different looking formulas that end up being the same, because they have to be the same, because they're counting the same thing. So this is an example of a combinatorial proof. So what I want to conclude with is just generalizing this. So let's replace 11 with n and replace k, or 8 with k, and see what these formulas become. And I'll let you check the details if you want to, but this first one, you end up getting n factorial here. This is n plus 1 choose k, and this is k factorial. And so this actually reduces to n factorial times p times the permutations of k things from a set of n plus 1. Actually, let me use a thicker thing to highlight that. And now let's see what happens if we, down here, if we replace the 11 with n and the 8 with k. So what we end up getting is we get k factorial down here. We get the number of permutations of n and k minus 1 right here. And then the last one, so if you multiply these two things, the 4 factorials cancel, and so you end up getting 12 factorial over 8 factorial, which in general is the number of permutations from n plus 1 objects of n plus, sorry, not plus, n, oh, no, it is plus, n, no, it's n minus k plus 1. So in total, so if you multiply these three things together, you end up getting k factorial times p n k minus 1 times p n plus 1 n minus k plus 1. So this is another way to count exactly what we did up here. So these two things, let me use that a different color. So these two things must be equal. So this is an example of a combinatorial proof where we get two very different looking things. N factorial times the number of permutations of k things from n plus 1 has to equal k factorial times the number of permutations of k minus 1 things from n times the number of permutations of n minus k plus 1 things from n plus 1. Okay, so that is probably harder. This is harder of a combinatorial proof than anything that we will do in the next lecture on combinatorial proofs. But I thought it's worth showing to you because it's interesting how we can count two things very different ways and get two very different looking formulas that have to be the same. So to learn more about this, stick around for the next lecture. See you then.